Well, it gives me great pleasure to introduce to you Dr. Jelena Kovacevic. This actually was the first time that I met her this morning, but I certainly know of her for years for her work. She's an international leader in signal processing. She did her PhD with Martin Beckerly at Columbia. And during that time or afterwards, they wrote this classic book on wavelets and subband coding, which is a classic in the field. And she's now at Carnegie Mellon, I believe, in the Department of Electrical Engineering, Biomedical Imaging. And she actually oscillates between Manhattan and Pittsburgh, I learned. So I'm very, very pleased that she accepted our invitation to come here. She's a busy person and a busy schedule, and for her to come to this, really appreciate it. And it's unfortunate that because of her schedule, she'll have to leave very shortly after her time. She'll participate in the panel discussion. So once again, thank you so much for accepting to come here, and please.
Thank you very much. It's a real pleasure to be here, especially everybody has been so nice. So I'm wearing two mics. I feel like I'm going to start receiving radio waves. So if I start, lighting up or something. So I like to move around. So if I start blocking the screen, let me know. I'm sort of this Mediterranean involved person. And by the same token, I like people to be involved. So please feel free to interrupt during the talk. I can cut a few slides if we get into a discussion. It's perfectly fine. So I have to apologize to Jeff a little bit because, he wanted to have this really nice big overview of image transforms in medical imaging. And I sort of spinned it a little more towards multi-resolution transforms. And I will give some sort of a justification for this, not only because I was lazy and I didn't want to overview the other ones, but also because I believe that they're actually making an impact today. And this slide sort of illustrates my philosophy. It's really a toolbox. So you have a set of tools that can be applied to many areas, amongst others to biomedical applications. And really what's important, and I think this goes with what our previous speaker said, is if you have a hammer, everything looks like a nail. What you should be doing, though these are not nails, and we make all kinds of assumptions to make them look like nails, but in essence they're not. So what you really have to do is really start from the nail. So you look at the nail and find the tool that you need to deal with this nail, right? And thus the toolbox of all various kinds of things that you could be applying to a certain problem. It's very important because fads sort of come and go. Wavelets could have been a fad, but fortunately they should prove themselves useful, so they stayed around. But when they started, there was a whole lot of people who sort of said, okay, I have any sort of ridiculous problem I can think of, signal that comes out of a noisy environment that looks like anything, and we're going to put it through this miraculous wavelet black box and something is going to come out, and then big surprise, it didn't work, right? Of course it didn't work. You didn't, you learned nothing about your signal, you didn't think about the problem beforehand, and maybe wavelets, and possibly wavelets, were completely inappropriate to a signal of that sort, right? So I think the big message here is really that you have to think about the problem you have before you start applying the tool. And that's really what I want to say. So the reason for using, when I say MR, I mean multi-resolution. This is the name that I actually like to use to call all these tools because they sort of fit into one big toolbox again. Even when I say wavelets, I think something more general than what you are probably used to thinking if you think about wavelets. Most often when people who are not familiar with this, when they hear wavelets, they think of a MATLAB function that implements an octave band, dyadic wavelet transform. You can pick the number of levels, maybe with dope sheet filters and so on. But this is really not the real power. The real power, I think, is in the fact that you can be adaptive, that you have a whole set of transforms that are sort of subsumed until this big multi-resolution hat, and then you can pick the right one for your problem. So this is the adaptivity. They have tons of other nice features that you might be able to use. One of them is localization in various domains, computational efficiency, and actually they have been widely used, or fairly widely used in medical imaging, at least in sort of research type problems. Though they have found application in a standard, the JPEG 2000 still image compression standard is really based on wavelets. So that's a nice thing. And actually, I remember being at a workshop in 93 or 94, and it was an image compression, and at the time, DCT was the ruling transform. And people were saying, why are you guys all working on these wavelets and so on? We have a standard, so what more can you do? And people said, well, there are options here. There are other things that you can extract from this signal. And sure enough, 6 years later, you have a new standard. So it's worth exploring other possibilities. So let's start. What is it that I mean when I say multi-resolution? And apologies in advance if I'm offending anybody with these extremely simple slides, but I'm a big believer in pictures, though, there is an equation underlying each one of them. I won't put equations. And actually, I remember Ingrid Dov, she once told me that she had to give a talk, and I believe it was National Academy of Sciences, and they asked her not to use a single equation. So she had to go, the mother of wavelets, and talk about wavelets, and she was not allowed to use a single equation. And she did a brilliant job, of course, so I'm just trying to get closer to that. So when I say resolution, because this is a loaded term, especially if you talk to people in medical images or biology, it can mean really different things. So for us, people who do signal processing, resolution is sort of roughly amount of information. You can be as precise or about this if you want, but roughly this is what it is. So if I asked you here, which image is lower or higher resolution? If I tell you, you need to have more information to really answer that question. But if I told you, look, they sort of look equally sharp, which one would you say is high resolution? Come on, anyone? This is a professor. Left one, of course. I mean, it's bigger, it has more pixels, it's equally sharp, so it must have more resolutions, roughly again. Now, what if I look at these two guys, and I think it actually shows on the screen. Which one is high resolution? Left one again. So who's going to tell me why? I'm a professor. I have to involve you here. I can't have you sitting and sleeping. No way, after lunch. So why is the left one? Why do you think one reason why the left one? Go.
Discern more of the features.
Exactly. And in terms of information, how would we say this? Those of us who have, learned Fourier analysis, what would we say? Probably that this guy has some high frequency components eliminated. So in electrical engineering or in signal processing, you would have said this image has probably been low pass filtered or averaged, blurred, smoothed, whichever way you want to call it, right? But now comes a tricky one. How about this one? And again, you don't have enough information to answer this, but you can give me answers and reasons, or reasons. Okay, so let's do the following thing, but I don't want you looking at your neighbors. Okay. All those who think that the left one has more information, raise your hand. 1, 2, 3 now. Okay. All those who think the right one has more information now. Okay. The rest of you, okay, so I'm going to give you 2 more options. All those who think they have the same amount of information. Okay. And all those who are sort of undecided. So you really, there is one, so you really fit into 3 bins. And again, it was an unfair trick question because I didn't give you all the information, but the third group was actually right. They have the same amount of information, except that they're represented differently. So this image is just an interpolated version of that image. So what you see is that information really doesn't have to do with size, right? It can be a very misleading concept. So the information is really something, if you want to think of it in Fourier domain terms, information is, let's say, the amount of frequencies that you have present in your image. Okay, now that we established this, I think I'm going to leave you alone for a while. So you can go back to sleep. So one reason why we like these types of multi-resolution transforms is that they provide localization. What does this mean? And I use this also for my students because it's sort of easy to get them into this. I went onto MapQuest and I said, I want to go see a movie on 68th Street in Manhattan. And this is the movie theater, Lowe's, Cinemax, whatever. And I can look at this map at different levels of, however you want to call it, different scales, let's say. I can look at it at the North American level, which is completely useless. I can look at it sort of at a city level, which is actually useful because I want to first coarsely decide where it's located so that I have a basic idea whether I go to the east side, to the left side, north, south, and so on. And then when I get there, I really want to have the street level to find out exactly what this movie theater is located. Now, this is absolutely the same for signals. So if I have a signal that has, so this is just a step signal here. And I want to find out where this step is located. The first thing I might want to do is I want to globally know where roughly it's located. So this here, which is really the first level of the wavelet transform, is going to give me, well, it's sort of located in this area, but I don't know exactly where, right? And then I can have these other details that are going to specify it more and more, depending on how detailed I want to be and how much detail I really need. So this one here really tells me, look, this guy is located at this point in time. Very useful. So it's sort of like having a telescope and a microscope at once. You have this zooming thing that you look at your signal and you can go up and down depending on what sort of information you want to extract. Okay. Now, I could do the same thing for images. So you can sort of zoom in on singularities, or singularities in images are, of course, edges. So if I have an image like this is the coarsest level, and this is the coarsest level. So I can have a global idea where these edges are, and this is what sometimes happens to these images. They get blurred. So you know that something is happening there. It's at some sort of an edge, some sort of a discontinuity, mathematically speaking. But you cannot localize it perfectly. So to do that, you might have to go to these guys here, these detail things, which really tell you, where these edges are. Okay, so how about this statement of characterizing singularities? Well, these transforms are actually very good at that. So you look at this signal here, which has a pulse, a ramp, and again a step, right? Mathematically speaking, and I won't use mathematical terms, but mathematically speaking, these are completely three different types of singularities. And they can be precisely characterized by using certain coefficients and exponents and so on. I mean, we don't have to go into this. If you look at the signal, you can see that, again, this is a coarse version of that signal, and then these are the detailed versions, what people call wavelet coefficients. You can see that each one of these singularities behaves completely differently when going across scales, right? The Dirac is here, and it sort of stays as an oscillating function around the singularity. The ramp is something that looks completely different. It has sort of a sinusoidal thing. And this looks completely different, and you can also see that the magnitudes of these things change across scales. And this is actually what people use to characterize these singularities. There is a famous paper by Mala and Zhong that they actually use this, call it multi-scale representation, which is very, very widely used, I believe, also in medical imaging. So one very, very good characteristic of these types of transforms. Another one that has gained popularity is that you can use it to separate signal from noise. So assuming that you have some knowledge of the noise a priori, or some basic assumptions maybe about the amplitude and so on, you are able to look at these levels, again, decomposition at various levels, and say, look, at this level, I really don't see much of a signal. Because again, you can characterize these singularities across scales. You can remove that part, which you think is a singularity, which is very important. Or you can just threshold things and say, below this level, I believe this is all noise. And do this at every level adaptively, and then you get a signal that's sort of clean from noise. So the red here is the original noisy signal, and the yellow one is the cleaned up. Now, why is this important? It is important because what people used to do when they were removing noise from images, they used to low-pass filter, because noise is something that's typically high-pass in nature, right? It's a wiggly thing sitting on top of your signal, annoying you to no end, right? When you low-pass things, yes, you're going to remove this noise, but you're also going to blur the edges, right? You're going to lose the sharpness. That's not good. You don't want that. So there are tons of methods that try to address this problem by removing noise, but at the same time sharpening or preserving the sharpness of the edges. Now, the edge, as we said, is a discontinuity or a singularity. So if I know that if I can detect that across scales there is a thing that consistently appears at the same point in time and has a certain behavior, I will conclude that this is a singularity or an edge, and I will keep that. I will make sure I keep that coefficient or those coefficients. And I can do this for many of them. And once I know this, then I have actually preserved my edges. It's quite ingenious when you think about it. It's a very intuitive concept. It's actually easy to explain, and it works remarkably well. So I believe that today these multi-resolution techniques, wavelets, and now even frames are becoming the standard for denoising, for removing noise. And originally this was done by many people, but it was really popularized by Dave Donahoe from Stanford and his thresholding techniques. Now, here is the really key concept that I would like to talk about. And interestingly enough, after so many years, actually, that wavelets and multi-resolution techniques have been around, it is still the belief that the wavelet is, again, as I said, this dyadic decomposition where the low-pass channel is split or where you progressively keep smoothing, as I showed you till now. But this is not all there is to it. What you really want to do, and this is my question, not what we want to see, but what is it that we want to answer? What I want to think about is that if I have a signal and I somehow represent it in the time-frequency plane, for example, we could figure out other planes of interest. But let's use those that we most often encounter. And I can find out that the signal's energy is somehow located in these blobs on time-frequency plane. Then I don't want to take again my hammer. This is my nail. This is my nail. Now I have to find a hammer that fits this nail. And how do I do this? I don't use now the Fourier transform. Why? Because the Fourier transform is just going to take horizontal slices in frequency. Right? And it will just split this guy in many things. Now, suppose I had a sinusoid, and I'll show you examples later. Suppose I had a sinusoid here. How do you think the sinusoid would look in this time-frequency plot? And BB cannot answer because he's an expert on this. The other people. So how do you think the sinusoid? Sinusoid is what? It's characterized by what? It's a line, exactly. So the sinusoid would be a line. So to extract the sinusoid, or to get, these are all representations. So I want to represent my signal in some basis or over complete expansion, where the coefficients are really the projection of the signal onto particular, let's say, basis functions or functions used in this representation. So if I have a sinusoid, it's great for me to use the Fourier transform. Why? Because there is a single coefficient that will extract that sinusoid. And when I see the Fourier transform, I will see a peak there. That's perfect. That's all there is to know about this signal. However, if I apply the wavelet transform to this, that will be really stupid. Because there will be tons of coefficients that would pick up this sinusoid. So here is an example where that would be not smart. Go ahead.
But this would not be the case, well, if you're talking about wavelets, then if you take an edge which is not aligned with the axes, then you will also have a problem.
Absolutely. So we're going to see all possible ways in which that's can be. You are actually nailing it now, figuratively. Okay. So the holy grail is really to find representations that are going to extract these blobs out of your signal. So here is what we would call, say, a trivial basis, a Dirac basis, and assume now that we're dealing with discrete time signals. So we're dealing really with samples. So this thing here is really sort of slightly misleading because it's really not continuous. It's not a continuous variable. You may assume that there are points here, though this one is a continuous variable, the frequency, right? So when I draw these little boxes, I'm sort of doing a piecewise constant approximation from this point in time to the next point in time, just so that you know what I'm doing. So when I say Dirac basis, this is really nothing but expressing the signal in the basis of Diracs, which occur at every point in discrete time, which means that the projection of a signal onto this, each particular Dirac, is nothing else but the value of the signal at that point in time. It's really trivial. But just to show you, in this basis, if you want, you see, you have perfect time localization. I can isolate any time local event. Any little wiggle that happens in time, I can do it. But I can say anything about frequency, right? Because it's spread over all frequencies. If I take a Dirac, the Fourier transform is what? A line in frequency, so it spans them all, right? Now, here is the Fourier transform. Big surprise, it's the complete opposite. It's a dual. So the Fourier is perfectly sort of localized in frequency. Now, depends how you want to do it. Do you want to do a series or you want to do the discrete Fourier transform? How well you are localized here. But you are. But again, the problem now is that we have completely lost the time localization because the sinusoids or complex exponentials have infinite time support, right? They appear everywhere in time. So when you start projecting, each one of them is going to catch every singularity that you have in your signal. So not to say that these two are not useful, or this one in particular has been our, bread and butter for more than 100 years, but you just have to be aware that if you have a signal like this, it's not going to work that well, right? This guy will be completely captured here, and you will know that there is a big contribution in this range of frequencies, but you will have no idea where this blob sits in time based on your Fourier coefficients, right? So here's the next thing. So people said, okay, so these sinusoids are infinitely supported, so we can localize it. Again, big surprise, you just cut them, right? Put some sort of a window on it, and that's short time Fourier transform, or some versions of it, Gabor transform. This is great too. So for certain particular things, this will work very well. The only problem is that once we do this, we have fixed the resolution both in time and frequency. Once we have chosen the length of this window, we have said, okay, in time, that means this is how well I can localize it. If the thing is a Dirac, I will know that it sits in this region, but that's all I can say. I cannot say where in this region it sits. Same for frequency. Okay, but it could be enough. It's definitely, I think, the move in the right direction, offering another possibility. And so here is what actually the discrete wavelet transform does, which uses a set of basis functions which you can shrink and stretch, and they become higher in frequency but shorter in time. So if I take the same function and say that it has wiggles, and I shrink it, I keep the same number of wiggles, thereby sort of increasing its frequency. If I stretch it, right, I make it lower frequency because I keep the same function, right? It's like an elastic string. And that's what happens. It is longer in time, but it has better localization in frequency. Now, question from this thing, it worked really well for this guy. Long in time, low in frequency. Short in time, high in frequency. What does the not work well? And, it's there. It does not work well for something that's localized in frequency but at high frequencies. Okay, so if you have a thing like that, do not use the wavelet transform. It's not going to work well. Okay, so that's, and you don't even see people saying this when they talk about the wavelet transform. They will give you all the positives but no negatives, right? So what could I do? I could actually have here the better localization if I know my signal is like this and sort of adapt it. So here is something that's called Wavelet Packets that was started by Koifman and Wickerhauser, Quake, and so on. And what they said is, what we're going to do, we're going to go to the finest level of resolution we can imagine, which could be, let's say, 1 sample wide or 1 pixel wide. And these are sort of trees. And then we're going to go up. You may imagine that this thing is iteratively built as splitting the frequency in halves, sort of octave bands. But so I can go up the tree and say, now I'm going to prune based on some cost measure I define, and figure out at each node in the tree, is it better for me to keep the parent or to keep the children? In other words, is it better for me to keep these two children here or to merge them into their parent, which is this whole area here? Okay, and but you have to have a cost measure associated. And when you do that, you can build sort of a signal adapted representation fitting your signal. That, of course, is the best. Right? And this is not one single transform. What's beautiful about this, that the wavelet packets, if it's a sinusoid, this thing would disintegrate into the Fourier transform. Or it will boil down to the Fourier transform. If this here is something that has low frequencies and is long in time, it will probably boil down to the wavelet transform. So in some sense, it will pick the right transform or the right representation for your signal. Key concept. Everything else you can forget. But this, for me, is important. And I have spoken to people today, and I have seen this many times. People will get entrenched into figuring out what type of a filter to use in the wavelet transform. That's a second order concept. Second order. This is the first order. If you miss this one, no matter what you do afterwards, you can't fix it. Okay, so this is the first thing you consider. You first find what fits your signal best, and then you worry about all these other things. How many levels, which filters, separable, non-separable, linear phase, orthogonal, all these kinds of things. Again, for me, these are all second-level concepts. And here is actually, this is on something I'm working right now on. It has to do with classification of images of locations of proteins within the cell. And this is possible now because fluorescence microscopy is so advanced, and the probes they use to mark those proteins are so advanced that people can do it even in live cells. It's really science fiction. But just to show you how these wavelet packets would look for two different proteins. This is a protein sitting in the endoplasmic reticulum, and this is actin, another protein, and the N sort of fell down. And you see, again, this is, when you look at these two images, the biologists who investigate those images, again, visually, they look at them and say, okay, this is actin, this is ER. In this particular case, they're very different, so you really can't say, based on your visual examination, which one it possibly is, based on shape and sort of where it is and so on. But there are some, for example, Golgi proteins that they cannot distinguish with better than a random chance. And the automated systems actually can have a classification accuracy of 90% on those. So what this says is that you are actually you are exploiting the information that's hidden there that you cannot see with the naked eye, which is, sort of the discussion we had before. Very important. And again, your point was well taken. You have to show people that this works. You can't tell them, oh, you have to use the scales if they have no idea what it is. But if I use it and I say, look, but this gives me better classification accuracy based on the ground truth I have, then they're going to say, okay, those tools are good, so go ahead and keep on using them. So that's sort of a challenge. But what's interesting here is you see, these are the types of images that you see if you use MATLAB and you use the wavelet transform, those of you who have used it. And typically they will split in 4, and then this one, the low pass, would split in 4, and then split in 4, and so on. But you see, this one just means that we have split it adaptively, meaning that the energy of this signal sits in this sort of space frequency subspaces. That's where it's localized. And this one actually was done for bioimaging. We have done the same thing. I might have an example for biometrics, which is recognition of your biometric characteristics to, for example, fingerprint recognition. If you want to go into a bank and you take your fingerprint and say, I am Jelena, and the system has to say, yes, you are, or no, you are not. Or I'm going to say, I'm an authorized user, and the system will say, yes, you are Jelena, thus you are an authorized user. Right? The same sort of a problem. Okay, so now we go back to these various representations. So here are the trade-offs in adaptivity, and this is something I mentioned before. So here is a very simple signal. I have a sinusoid, which is sampled. I just put the envelope there so it's easier to see. And I have a Dirac, or a pulse, at some point time 0. And here is what happens if you take the sort of a Dirac basis. Of course, the Dirac will extract this guy. But this sinusoid, there's no way you can see where it's located in frequency because it's spread over all frequencies. By the same token, if you take the Fourier transform, it will isolate the frequency of the sinusoid within a certain region. This is where it's highlighted. But you have no idea where the Dirac is because it's spread over all time. Right? So here is what the Gabor would do, or short-time Fourier transform. You do localize it within a certain time window, and you do localize it within a certain frequency window, but not better than that. And in this particular case, the wavelets do a great job, because here at high frequencies, I localize it with a short high-frequency wavelet, and at low frequencies, I localize the sinusoid with a long low-frequency wavelet. But again, if I gave you, okay, so I'm not going to jump ahead of myself, which I tend to do. So let's see this. So here I have done exactly the opposite. I have taken the high frequency now, sinusoid, and I have put the Dirac there. By the way, I just wanted to tell you, all these are produced in MATLAB, and I gave Jeff my talk with the notes attached. And the notes tell you exactly which functions to use to produce these plots. So if you want, you can do it on your own, if anybody wants to entertain themselves by doing this. So you see what happens here. These are the time frequency plots I actually showed you before, is that you do localize the Dirac. It's fine. It shows up everywhere. But you see this sinusoid now, because it's high frequency, it's spread over all frequencies. You can see sort of that it's a sinusoid because these coefficients are stronger and you know, weaker, right? And here is if you have a lower frequency, then you still localize the Dirac, but you localize your sinusoid better because the window in frequency is shorter. I think this is quite a nice example of illustrating that. So let's see if I take, again, the lowest frequency sinusoid plus a Dirac and see what happens the discrete wavelet transform and what happens with short-time Fourier transform and Gabor. Okay, so we have the same story, right? These fine wavelets would isolate this guy very well, and the sinusoid will be isolated fairly well here. Now, the sinusoid in the short time is isolated fairly well again, okay, because it fits within the window that we set there. However, that's not to say that we haven't isolated the Dirac, but we have isolated it to a certain window. You see that this thing has a width, right? It's wider than that. That's because I have no finer time resolution than that, you know, available to me. Okay, so here is the same just sort of illustration how this would look on images, how things are localized in certain space frequency regions. And also the whole talk is, Jeff has it, so maybe you can put it on the web or something if anybody wants it. So now we finally come to the question, okay, this is why. These were all whys, why we would use multi-resolution, and I hope motivated why we would use something like this. And now how would you use it? I'm supposed to finish at when? Like 15 off, 10 off?
Yes, 15.
15, so I have sort of 10 minutes. Okay, so this I'm not really going to go into very much. There's lots of math behind it. It's basically a basis representation. So this picture was really made for people who hate equations so they can look at it as images. So this really is your projection of this thing onto this basis function. It's kind of nice to see it visually too, because mathematicians actually most of the time don't think that way, right? And these are now projections of this thing onto subspace, let's say, of coarse signals and the details needed to go between this guy and that guy, okay? And if you want to, I love to look at matrices again because they're visual. If you do on a finite compactly supported signal, you can do the same thing. And here is really what happens. These are your basis functions. And in this case, as you can see, I have picked what as basis functions? I have picked har in both dimensions. So this is 1 everywhere. This is 1 on the left and -1 here and so on. Okay? And this happens on the synthesis side. We can reconstruct the signal if you want. We can forget about this. Now, it's important to note here that these representations can have many flavors. And here comes maybe a level 2 consideration. Which kind of a representation you want to use? Okay, so first let's consider basis. Non-redundant representations. And you can have orthonormal basis or you can have general basis, which we call biorthogonal basis. And the questions are, why would you use one versus the other? Well, besides obvious mathematical elegant properties, let's say, of an orthonormal basis, which I'm sure you all know, there are some practical considerations into this. Actually, when you implement the system, having an orthonormal basis is more convenient because the filters that you use are basically the same. They're just time reversed. There are lots of other things. You have no issues in reconstruction. It's always stable. There are usually no numerical issues. There are lots of things that you can say there. And moreover, as we all know, because it's an orthonormal basis, it preserves the norm. So the L2 norm is preserved throughout the system, which for the engineer means the energy of the signal is the same at every point in the system, which again, for the engineer, it means that if I perturb my signal a little bit, I have no fear that something will blow up in the system. Very nice. However, having said all these positive things, there are drawbacks with orthonormal basis. They're very constrained. Essentially, if I look at it in a plane, there is really only one. All the other ones are rotations or unitary transformations of the first one. So How good is that? Well, it could be good or it could be bad. Well, this offers me a whole host of choices. I have infinitely many, which are absolutely not similar to each other. You have those which are very close to orthonormal bases. You have those which are very far away. You can obtain, let's say, practically speaking, filters which are different, maybe having symmetries, which might not be possible in this case. There are all host of considerations that you might want to think of. Okay, now, how do we implement this? I just want to give to those of you who are not familiar with this just a glimpse how these transforms are implemented. The basic block is really, or a device is called a filter bank, which has these band pass filters, which are the smoothing and differencing operators, where the signal gets split into these bands. And here, really, at these points in the system, you get these projections onto these subspaces I was talking about, of, let's say, coarse images and detailed ones. And this is how the time frequency representation of this basis would look like. These guys now denote my basis functions. So they are short in time, but they split the frequency in half, which one can see here if you imagine that this is low pass, this is high pass, which means you have fine time resolution but not great frequency resolution. This is sort of the next step you could do after the Dirac basis to make it better in frequency. And again, this is what you could do with this sort of a representation. You can look at this on the web. I don't want to go into this right now. What else can you do? You can do sort of the short time Fourier transform is implemented like this. It's a full-size tree grown up to a certain number of levels. And as you can see, then you really split just the frequency into uniform bands, but nothing happens in time. And here are examples of what happens to the signal. Again, we went through some analysis of these ones before, so I won't. This is how it would look actually to the image, right? It gets split into these even bands in space and frequency. What else can we do? So here is the discrete wavelet transform. This one uses the filter bank iteratively on the low pass channel, so it keeps on splitting the low band, meaning it keeps on smoothing the signal more and more. You get coarser and coarser version of it. And here is how it works, you know, on 1D and 2D signals. And here is the thing that I was talking about, the adaptive one. So the first thing you do is you grow the full tree, you split it like this, and then you start asking yourself, is this good? Is it better for me to keep these guys like that, or I want to merge them? In which case they actually become shorter, because this tree is not that deep. That's how you get them shorter. And maybe I get something like this, where all these sort of dotted lines have been erased from the tree. So you have a subtree of your original tree. And here is just sort of an animation, and I put it here because Jeff liked it, so I thought you might like it too. So here's what you do. You split an image into 4. Let's say this is a simple example. And then you keep on splitting each one of these. I just show one. And you get this final split to a certain number of levels. And then you prune. So you ask yourself, is it better for me, is the cost of this parent, keeping the parent larger or smaller than these 4 children? And in this particular case, it turns out that the parent is cheaper, so I keep the parent, I get rid of the children. And I keep on doing this with the other ones. And, you know, I sort of adaptively build this tree that sort of then divides the image into these adaptively chosen subbands. And this is how it looks. We have seen this example before. This is the example I told you about just to see it on some different images. These are fingerprints. And if one looks at these, I mean, to us, they all look the same. But, you know, you and I have quite different fingerprints. We know that. And if you build the wavelet packet representations, you see that they are all different. These are 20 different classes corresponding to actually 10 different people with 2 different fingers. So there might be me here, but with 2 different, I'm not there, but I'm saying that's, you know, one person with 2 different fingers. I think a thumb and something else. And you can see that some of them are quite difficult because they get blurred or they get rotated or they get moved and so on. So there are tons of issues to consider actually in a real problem. And finally, I wanted to talk about frames, but I think I'm going to skip this because there is not enough time.
You still got 7 minutes.
Oh, I thought...
50.
Oh, 50. Oh, okay, good. So I'm going to talk about frames. So if you thought you were off the hook, sorry. Jeff just, you know, made you sit through 7 more minutes of me. which, believe me, it can be too much sometimes. Okay, so one thing that I wanted to mention, we talked about bases till now as representations, but nobody stops me really from considering over-complete representations, which in many cases is an advantage, and I will say when it is an advantage. So a simple example is considering the real plane. So if I took a basis in real plane, let's say take an orthonormal basis, and if I add an arbitrary vector to this, really it doesn't hurt me at all. In a sense, if I could represent my signal before, I can certainly represent it now again. But there are advantages for using something that's redundant, because this is a redundant system. I have more vectors than I need to represent any point in this plane. And what are the advantages? First of all, there is more freedom in design, right? This is not as constrained as our bases are, right? Because I am now over-complete. The bases have to hit two different spaces in 2 dimensions, subspaces. If I miss one of them, I'm stuck. Okay? Here, as long as I have 2 of them that are linearly independent, I can put the third one wherever I want. So this already gives me something. It is robust to losses. If I lose one of the projections onto one of these basis functions, I can still recover because I have 2. And that's a big deal in some of the things. For example, your projections could be corrupted by noise. There's lots of noise everywhere. Your projections could be lost, when transmitting them, let's say, over the internet. Some coefficients are lost. You still can reconstruct. You're paying for it by introducing redundancy, but you're gaining something. And another thing that's important, which I'm not going to go into because it's a little more difficult to explain, is shift invariance. The typical techniques that people use are usually shift invariant, meaning if I put a signal, let's say I take an ultrasound of my bladder, and I put it through the system, and I get some output, which I'm going to analyze. Now, if I shift this image just by a little bit, so I move, the ultrasound, 1 millimeter up, I really want my output to sort of be moved 1 millimeter in some domain. I don't want to see something completely different. So I don't want to put, a shifted version of my bladder and get an ultrasound of my heart. I mean, it's a ridiculous comparison. But this is really what happens when the systems are not shift invariant. And the bases, the discrete wavelets, introduce shift variance into the system, which is one of the things that people try to solve when they actually deal with wavelets in medical imaging, because it's an undesirable property. And frames can actually take care of some of these problems. And just to show you how this looks like, so bases, you can think of bases sort of as square matrices, right? You have the same number of projections as the dimensionality of the space. So if I put a signal of a dimension n, I will get n projections outside, either for orthonormal bases or general bases. If I do this with frames, I really think of it as rectangular matrices. So I put n-dimensional vector in, but I get an m-dimensional vector out where m is larger than n, for example. Okay? Then I go through the system, and then I reconstruct back to my n dimensions. And there are tons of reasons why you would do this. One is robustness to noise. And this one is actually easy to understand. So think about it that there is, let's say, electrical noise from some instrument that you're using that's superimposed on your signal. So if I have 2 vectors and the noise gets distributed over these 2, this is worse than having the same amount of noise distributed over 3 vectors, because now the average amount of noise per vector goes down. So it's easier to clean, right, on each vector. And this is the reason why frames are becoming very popular in denoising, roughly. There is robustness to erasures, as I mentioned, and these are some properties of frames that might be of use, but we don't look at this. So I'm going to conclude now just with a few final remarks that are actually sort of biomedical specific. So when you have all this wealth of transforms that we have seen now, all these tools, which ones to use? So which one is the hammer for your nail at hand? So you have to look at the properties of your signals. You have to look at the properties of the transform, as well as the task you want to perform. Do you want to segment? Do you want to enhance? Do you want to register? What is it that you want to do? Okay, so properties of, let's say, bioimages, biomedical images. There are many that are different from the natural images we see when we take a camera and take a picture of something, landscape or something. One is that there's tons of noise of all kinds and types. And with sort of these trend in medical images to be less and less invasive and having more and more methods that are more and more non-invasive, you're actually going further and further from the source, right? So I am, and this is my lay, image of the thing. So if I perform the surgery, I can see the actual source. I can measure something on it. I can see it. I can fix something. If I do it on the surface of my skin, this is quite different, right? So you're getting away from the source maybe. And this introduces, and then other levels, other types of noise that you think about are instrument noise. You're digitizing things, you're measuring things, ambient noise, just power noise, all kinds of things that happen. Lack of ground truth. In many of these problems, we don't have ground truth. We use something that, so what's really interesting is sort of it becomes an ill-posed problem. In many, say, segmentation problems in medical images, your ground truth is something that we humans, let's say, doctors, have drawn by hand because they can see it. But who says that's ground truth, right? And we are comparing the methods to something we don't know is correct, right? So this is one problem, and there is no particular answer to this. In this particular problem, we are also doing segmentation of these cell images. And again, as ground truth, we are using hand-segmented ones. But what other people, my colleagues are doing, they're going to tag the plasma membrane of the cell. And that's going to be real ground truth, right? So if I have a tagged membrane, I tag the protein sitting on the membrane, well, that really tells me where the boundary of the cell is, as opposed to me looking and trying to figure it out. So if you can have some sort of a better ground truth, that's always great, but you don't have. Large deviations, populations, if you do these things on people, the range of normal and the range of abnormal is huge. So you have to have algorithms and transforms that operate well on a very wide range of conditions. This is not something we are used to. Low definition and contrast. Again, these images don't have sharp edges. They don't have high contrast. They have all these kinds of problems that you have to overcome, and maybe helps do this, as we have seen before. You try to enhance. And then, a whole wide range of wide time and frequency localized features happening. For example, if you look at the signal, which is an EEG, and you look at patient with epilepsy, you're going to see spikes that denote epileptic seizures. You see actually longer ranges of certain frequency oscillations that also denote. So you have all kinds of things that you have to consider. And so in terms of transforms, now that you have considered what kind of a signal you have, there are all kinds of properties apart from adaptivity. Which one of these adaptive transforms you're going to use, right? Is this a finite signal? If it is, you have to deal with boundary effects. And this is actually a mathematical problem. The representation type, is it redundant or not? Am I going to use bases or am I going to use frames? Most of the time, if you don't have to reconstruct, no need to go for bases. There are two constraints. Don't use the wavelet transform when you don't need to reconstruct your signal. Go use a frame. Use something that offers you more freedom. Am I going to use orthogonal or orthonormal bases or tight frames, which are sort of generalizations, versus general ones? Again, is this an issue of computation? Is computation so important that you need to take, not to have to invert matrices, for example, which happens for general bases? Properties of basis functions, how important are they? Do they have to be symmetric for some reason? If you deal with images, typically you should be symmetric because, left and right and up and down in images don't make sense. Though many times we consider images actually as time signals in 2 dimensions, which is completely wrong. Images are not like that. They don't have, unless you are acquiring them somehow and there is a time information in it. But otherwise, this is a silly thing to do, really. Issues when you go to 2D for images. What sort of a sampling lattice you might want to do? We all use rectangular, but it doesn't mean that's the only one. When you start using other lattices, you have whole other issues to consider, and some of the properties are much better suited to our visual system than the rectangular ones, such as the quincunx sampling lattice. Basis functions, again, separable versus non-separable. real versus complex. You want basis functions that have some orientation selectivity. We have many of these wavelets around. So each one of these things you sort of have to ask yourself before you even start attacking the problem. And finally, what is the task you want to perform? It's very important to connect this to the transform properties of your signal. And I think I am done. So to conclude, I would just say that this multi-resolution toolbox, which includes all kinds of transforms, is very rich to attack a whole set of problems, but again, think about the nail and the hammer, and think about which way you go, hammer to nail or nail to hammer. So I think at this I'm going to conclude. Thank you very much.